So how would you prove it? Well, you start from any point. So you want to prove that this point is actually worse than this point, okay, where the function is maximized. So what you could do is you construct a path from this point to that point. So you cleverly construct some path that goes from this point and eventually becomes that point, so that this function value is monotonically increasing along that path. Okay, so you kind of change the original problem to kind of a derivative problem. So you say that I'm only going to look at the function as you move along this path. And if you can show that the derivative of the function is positive, then that means you have shown that the function is increasing, and you reach this point, and no matter where you start, you can construct such a path where the function is increasing, and the moment you reach that point, it must be that that point is the best possible point. Okay, so now you don't really have to worry about the function landscape. Yeah, but you're not following gradient descent, you're following some other path. So you're constructing a path which is not looking, it's not gradient descent, it's just some path that you have cleverly constructed, which you know it starts from here and it ends there. So it doesn't have to look at the function before. So I can tell you roughly what the kinds of path that you use. So let's say x is a random variable, and you want to convert this x to a Gaussian. So what you would do is you take z to be a random variable with the same variance as x, and you look at this path, square root tx plus the other way, square root 1 minus tx plus square root tz, where z is a Gaussian that is independent of x. That is x. So now this is a family of distributions or family of random variables that at time t equal to 0 you start at x, at time t is equal to 1 you land up at a Gaussian. So if this point was x and this point was z, then this is giving you a path that is slowly morphing that x into a z. And now if you were to say plug in this into this function evaluation and show that along this path the function is monotonically increasing, then you get the answer that therefore the function is maximized at Gaussians. And it doesn't matter where you start. So if you start at some other point, say x tilde, you would construct the same path, square root 1 minus t x tilde plus square root tz. You'll again get some path, you'll again prove the function is monotonic along that path, and then prove that the function evaluated at z, which is that Gaussian point, is more than the function at any other point x that you care about. Okay. So it's just a way of showing that there is a way to optimize these functions if you already know what the answer is going to be. So if you know that if you know this is where this ought to be maximized, then you could cleverly construct ways to prove that yes, this is maximized there by constructing these kind of monotonic paths. Yes.
You will not, such a path will not exist. So in general, the existence path implies that there is some kind of unique maximizer in some kind.
I see. So, right, yeah.
So you know you have to maximize something for you.
Yes, yeah, I guess, yeah. If it's a local maxima, even this path will say that you move along this path and you won't get a positive derivative. So the fact that this path is giving you a positive derivative means that you don't have these, or you don't have a local maxima that has zero derivatives everywhere. You might have zero derivative in some directions, but in that particular direction, you don't have a zero derivative. Yeah. Okay. So 10 minutes. So this is now a 5-minute introduction to, I think, what Chandra will explain more tomorrow. So this is a way to, this is a different way to solve optimization problems of this kind. So you have a function defined on the space of distributions and you want to optimize it. You want to say that this is maximized at some point. The function is very badly behaved and you don't know whether it's concave, convex or anything of that sort. So let's just draw a picture. So let's say your function looks something like this. It's not at all convex or concave or anything of that sort. And you want to try and maximize this. So one way to maximize this function is not look at this function really, but to look at a function which is its upper concave envelope. Okay, so you look at a function. So think of, you take a piece of string and you put it on top and you stretch it really tight down the below. So you're going to get a function which is this dotted function. Oops. And this. So this is the upper concave envelope of your original function. So your original function was bad, but of course your upper concave envelope is going to be concave by definition. And maximizing the original function pictorially is the same as maximizing the upper concave envelope, because if your function here is maximized here, the upper concave envelope is going to touch that point and it's going to be the peak of. So maximizing the original function is equivalent to maximizing the upper concave envelope. Okay, so that's the idea. So what happens in case of the entropic kind of functions is that you have a function capital F. So capital F is a function from, say, random variables. So I'll just say from Rn valued random variables to R. So you can often define a lifting of this function to R to the 2n. So you instead of f of x, you now define f on R to the 2n valued random variables. And this extension or this lifting is often quite obvious in our entropic kind of things, because wherever you see h of xi, you just put h of xi1 and xi2. Whenever you see h of bjx, you say bj of xi1 or bj of x1 comma bj of x2. Okay, so this lifting to a higher space is something that is very obvious in most information theoretic expression. And the key kind of step in optimizing these functions is proving a certain subadditivity result. That if you were to lift this function, then this function on this higher space is somehow upper bounded by its marginals in the lower space. Okay, and okay, so in 5 more minutes, I'll tell you, I'll try to quickly get how Gaussians come into the picture. So just to explain where this trick came from, so this some idea of this was used in the original proof by Lieb in the Braskamp-Lieb result, but it was kind of still known to the math community. Then Chandra wrote a paper with a student in 2014, where he kind of translated the trick and used it in an information theoretic setting, and that's where I got introduced to this trick as well. All right, so the key step was proving this kind of a subadditivity result, and then there is a very clever trick which is called the rotation trick. Okay, so what you do is the following. Let's say the function was optimized at some point x star. So let's say x star is the optimal value or optimum point. So you take two independent copies of this optimum value. So take x1 star and x1 star and x2 star are IID copies of x star. Okay. Right, so start with the so we are kind of trying to establish some kind of result about the optimum value. You say let x star be the optimum, x1 star, x2 star are IID copies of that optimum. And then you say that let's say f of x star is also equal to some m. Okay, so now you have a series of inequalities. First you say 2 times m is equal to, or rather let me say f of x1 star comma x2 star is equal to f of x1 star plus x2 star by root 2 comma x1 star minus x2 star by root 2. Why is this true? Because often when we are dealing with entropic expressions, rotations don't change entropy. It's a one unitary transformation. So whenever you're looking at expressions which are h of something minus h of something, this particular operation does nothing to it. So further, this you can also show that when x1 star and x2 star are independent, um, the value attained by f of x1 star comma x2 star is 2 times the maximum value m. Okay, so at this step you use subadditivity and say that, well, this has to be less than f of x1 star plus x2 star by root 2 plus f of x1 star minus x2 star by root 2. And each of these in turn has to be less than m because x star was the optimum. This is not known to be the optimum, so this is less equal to m. Okay, so what we are essentially saying, we are starting with 2m, getting a series of inequalities and ending up again at 2m, which means that if x1 star was the optimum, then each of these two values should also be the optimum. This has to be equal to m, this has to be equal to m. And now you can use central limit theorem. So you say that if x star is the optimum, x star plus its identical copy divided by root 2 is the optimum. Well, you can keep doing that again and again and again and say that, well, you'll eventually reach a Gaussian, right, when you continue this process. And that essentially tells you that it's enough to look at Gaussian. Okay, so we started with some property saying if x star is the optimum, then there is going to be some Gaussian which is achieving the same value as that x star. And this particular step, the key step is the subadditivity step, where you show that this f function satisfies this subadditive property. And
but you're saying that you are very general, like you have stability and you have f and Gaussian always.
Well, we are also using this step here. Like the rotation is not changing anything. The function value is the same when you rotate your distribution. Yeah. Yeah. So under independence, it's additive. Yes. Or under any general joint distribution, it's subadditive. Under independence, it tensorizes, so it splits up exactly. So that's why you have this equality, the tensorization. This is because rotation is not changing the function. This is because of subadditivity. And the last step is again because, well, m was the maximum, so each of these has to be less than m.
There is something that I missed in the beginning, which say that f is on the variable.
F is.
So you say that f is working on the variable, right?
F is working on Rn valued random variables, yes.
But then, so that's the expectation anyway, or not?
When I say working on the space of Rn valued random variables, it's working on their densities. So it's just a function of their densities.
You are working
on the distributions, yes. Yeah. So it's a function of densities on Rn. So
let's say
it's a density star, yeah. Yeah, yeah. You need the unique property of a Gaussian is that if you rotate it and they still remain independent, then they have to be Gaussian. And that is actually happening here because when you get equality everywhere, this joint distribution is tensorizing, which means that they are actually independent, so it has to be Gaussian. Or you could just ignore that part and say that I'm going to use central limit theorem. And so this, the earlier proof which says that when you rotate things and they still become independent, they must be Gaussian, is to prove that Gaussians are unique. But if you don't care about uniqueness, then you might just say, well, start with x star, it's enough to look at a Gaussian that is generated using that x star. Okay. So I'll just stop here and say that this particular optimization trick happens to yield a proof of both the Braskamp-Leib and entropy power inequality by using the same kind of steps, which makes it possible to combine them and also yield this general result. And the general result was that whatever expression I had written before, you get something more from it than what you get, yeah. So in particular, there are some classes of inequalities called Zamir and Feder's, some entropy inequalities where you're taking linear transformations of random variables. But if you now allow some dependency between the random variables, the existing inequalities don't give you any reasonable bounds. But these inequalities at least give you some correction terms using mutual information kind of correction term. So it gives you some more classes of inequalities that you won't get using just these two of them. Yes.
go back from entropic form to functional form for this?
Yeah, so the question is like, is there a corresponding functional form for the EPI itself?
Or maybe you are this one.
Yeah, so if I could get a functional form of the EPI, then I can explore functional forms of the other one. But it seems that the functional form of the EPI happens to be the EPI itself. So you don't get anything new if you go to the functional space. Or rather, the EPI actually emerges as some limiting result in the Proskaup-Leib inequality. So I'm not aware of a functional form of the EPI, but if you try to get a functional form, you end up getting just the EPI again. That's what.
Braska, ELI is a special case of that they let's call this inequality the last equality.
Yes. That's a BL EPI. Yes.
And the ELI has a special form. Of course, in the case of restricted version of EI, it's of fetal rate. But in general, that doesn't mean that it should not have.
It does, yeah. But my thinking was that if a special case of this BL EPI is giving me a functional form, another special case of this is the EPI. So if I were to get a functional form for the EPI, then that gives me reason to believe that there should be a functional form for the whole thing, the final expression. But I'm kind of sure that there is no functional equivalent of the EPI itself, because you end up getting the EPI again if you go through the duality procedure. Yeah. Okay, I think I'll stop here. 3:35.
Okay, so then we meet at 4 o'clock at the auditorium, and then the tea right now.
Confused. So, two questions. You were mentioning that instead of maximizing the function, you can maximize.